I'm going to record it for everyone who can't be present at the moment. Okay, so if there's no questions on those, then I am going to start with our very first section, which was everything we did leading up to midterm one. And that was all wavelengths and how light has both wave and particle like functions. So, starting off, know your constant. Speed of light comes into play quite a bit. Know what the wavelength is, how it's from crest to crest or trough to trough, or one of those two. Either one works. Um, I found for me that was good to have this memorized, this little chart about the light spectrum or wavelength spectrums, because on the first midterm there was a couple questions that said what wavelength color does this correlate to. So just know that visible light is anywhere from like 400 to about 700, and that for 400, 500 is going to be your very high energy purple and blues, and then 700, anything that's kind of like above 550-ish is going to start getting to the red zone. And then hopefully everyone knows that infrared is after, and then ultraviolet is before, because we deal with those ones too. Everything else I don't think we've really mentioned, or like hasn't had a big effect, so we don't really need to know it that much. But another good thing to know is this formula, that the speed of your particle, the speed of light, is equal to your wavelength times your frequency. And then this is the speed of light constant, for anyone who's wondering. And if I'm going too fast, you guys can ask me to slow down. Okay, so the next thing that we basically talked about was quanta and photons, and that's just the idea that as we get into very, very, very small objects, they start coming in basically packets of energy, so we can't look at them like just as we do in physics, just as large objects that have constant motion or constantly move in a wave-like fashion, because now when you get really, really down into it and you look really, really closely, like he said in his lectures, it's all done in little quanta, the little packets of energy in like these discrete amounts. And he had a really good example for understanding that, was his little water bucket. And if you pour water into a bucket at a constant rate, it looks like it's always flowing. But if you slowly limit how much water you pour until you're just pouring one single H2O molecule at a time, you'll start to see that if your bucket is on a scale where you're poured into, you'll start to see that it starts jumping, which is those little packets of energy, those little packets of the molecules and stuff being added each time. So it's really just something that's very, very small, but it's so small, I guess, at this point, that we can't just think of it as a constantly moving, constantly flowing form of energy. And then, okay, let's see. Blah, blah, blah. So the thing to know about that is that photons are absorbed and emitted in these little discrete units, which is basically what we did the entire up till midterm one, is what we dealt with, the little photons, the energy of a photon. And then the energy of photon formula is E equals Planck's constant, which I think is on your equation sheets, but if you want to know what it is 6.62608 times 10 to the negative 34th joules. And then this little thing again would just be your frequency. Sorry, it looks so much like a V, but it's not. So the first thing we ended up talking about was the photoelectric effect, which was basically if you were in a vacuum and you were shooting the UV light at that sheet of copper, that sheet of metal, then you would have electrons bouncing off of it. But that's only if your energy of the photons of light were sufficient enough to remove the electrons from their atoms that are in the copper. So that correlates to these equations where basically we have the photon energy, so E equals hv. So in this case, it would just be hv as your energy, minus the work function, which gets referred to as the threshold energy. So if it ever says the threshold energy for removing an electron, that just means it's the work function. And basically, that's how much you have energy you need, the least amount of energy you need to actually remove one of these electrons from, if our metal is just copper, then remove it from a copper atom. And that's going to equal our kinetic energy, which is just energy in motion. So that's just 1/2 mass times velocity squared. And I don't remember the mass off the top of my head, but I think it's like something to the -14th of an electron. So this equation definitely comes into play a lot. It came into play quite a bit for studying for that midterm and on the midterm. And if you ever have a case where you have 0 kinetic energy, then that means that your energy of the photon is going to be exactly equal to the threshold energy of whatever atom you're trying to remove. So if it ever gives you a question where it doesn't give you kinetic energy, it says the kinetic energy is 0, then it asks you to find like either the photon energy or the threshold energy. These two are equal. And the big point that he tried to like hit home with this is that you have to have sufficient energy to be able to remove your electrons. If your electron was not sufficient, like the entire point of this experiment found out that if you don't have enough energy in each of the photons that are hitting and interacting with the electrons, nothing's going to move. And you can make your light as big and small as you want, but there's no electrons that are going to be released. So that whole theory proved that light doesn't just travel in waves. It also travels in these little quantum packets. And then those are our photons. And then this is just talking about sufficient energy needed to remove each electron. And in the case that you do have sufficient energy in your photons, which means that you tend to have a decently high frequency of them or a very small wavelength, and you decide to make your light bigger, then however many times you increase your light source is how many more electrons you're going to increase ejecting. And then this all came into play about visible light and how we see it. And the visible light we see is just when a photon interacts with an electron, the electron gets really excited and it jumps levels. So it'll go from its N1 shell to its N2 shell. Or if you have sufficient enough light, it'll jump higher than that. And what we see when we see light is the electron is going back to its ground state. So it's losing that energy and it's throwing off the proton and it's jumping back down to its original state. So anything that's not in its ground state can just be considered excited. So if an electron jumps from N1 in this case to N2, then when it's at N2, we can just say that the electron is excited. And then it would just fall back to its ground state when it couldn't stay that much longer. And then again, we see our difference in energy is Planck's constant multiplied by our frequency. And this is just the Bohr frequency condition, which might get referred to. I doubt they're just gonna tell you to use the Bohr frequency, but you should know what this is because it's important. And then what happens when we see all the different emission lines is that um, there is certain energies of the photons that need to interact with the electrons for it to have any effect. So whatever interacts, it has to bridge this exact gap. Like it doesn't want to be over, it doesn't want to be under, it wants to be exactly this. So that's why we only see spectral lines, and that's why spectral lines are unique to every single molecule and every single atom, is because each atom, each molecule has different different energy levels specific to that atom or molecule. So if they ever ask you a conceptual question that's saying, oh, can we actually tell what atom this is or what molecule this is based on the spectrum lines, you can say yes. This is just repeated. Okay, so Rydberg's constant, basically, if you want to find the change in energy as this electron jumps from its N1 to N2 or whatever it is, then this is how you would calculate it, except you would have an equation that looks more like Rydberg's times Planck, so R times H over N2 when N is your final value, minus R times H over N2 when N is your initial value. So in the same sense of we're just finding, if you've ever found displacement or change in time, it's just final minus initial. And I actually have a good question for this that we can practice on from one of the his little study videos where you actually have to convert this to not hertz, which I just thought was weird, but maybe that's just me. And then in the case that your total energy, your total change in energy is negative, it's just saying that when your electron is actually bound to the atom, it's going to have a lot lower energy than a electron that has been set free and is now moving or has been ejected. And normally when something has lower energy, it just means that it's more stable. So when we look for reactions and stuff like that, we're looking for stuff that has a little more instability. So anything that's willing to like really give an electron or take an electron. Okay. And then here it is again. You just want your final minus initial for the change in energy. And I think, yes, this is the right page. Okay, so we left off right about here. So now we're getting into, that was all about the quanta properties of electrons and atoms and stuff like that, in the sense that you have little tiny packets of energy, but they're actually a mix of both wave-like properties and quantum properties. So in this case, one of the wave-like properties that we can see is diffraction patterns. And basically what constructive and destructive interference means is that constructive, the wavelengths are going to line up and the frequencies are going to line up. And therefore, overall, you get this much larger amplitude, more powerful wave. And destructive is just saying they're not going to line up, because if you can see here, this is the trough while this is at its peak. Then they're just going to cancel each other out, and you're going to get a lot weaker, a little bit weaker of a wave at the end of it. And the way they just figured this out was they shot little light photons through little tiny holes, and when they would interact with each other, we would see them go farther or change direction or something along those lines. And then this would just be the result of the diffraction patterns. I don't think we really went over anything like that on any of the tests, but you never know with Lebel. Okay, so one of the things that probably is going to be at least mentioned in one or two of the questions is the de Broglie equation, and that's just saying that the wavelength is equal to Planck's constant over the momentum when momentum is mass times the velocity. And then a good thing to know, because there was a question on one of the midterms that asked if something along the lines of a car maybe would be able to have wavelength properties. But the thing with wavelength properties is that if an object is too big, we're not going to be able to see those wavelength properties. So it has to be decently small to be able to actually see and measure and recognize those wavelength properties, or else we're just going to see it as moving with the physics definition of science, where it just moves. There's no waves or there's no jumping around. He went over this reasonably quickly. It's just the quantum mechanical description. And the whole idea was that electrons have discrete energies with only select wavelengths. And again, that's kind of due with electron can only jump a certain amount. So you have to have that select energy in whatever wavelength it is match the distance between the N1 and the N2 jump. And this kind of helps explain why we see these select, oh, each electron has a specific energy state. And then here he talked about it again a little bit down here. So again, momentum was just, if momentum is P, then energy can also be measured as momentum times the frequency. And you get this entire equation where you can kind of break it down. So if you take that equation and you know that E equals H, or Planck's constants times frequency, and you know that frequency is also, from the equation, the speed of light equals the wavelengths times frequency, we can end up getting an equation that looks like this overall. So I've seen this a couple times. I don't know if we ever really did much with momentum, but it could be on there. And then these three fundamental equations actually build on each other. So based on this momentum, the Heisenberg's indeterminacy equation just says that, oh, if we measure at 2 points, we have 2 points where we measure when a particle passes through, and then we measure again when the particle passes through its second sensor. Well, we know the time that it took to go from here to here, but we don't actually know the distance because these particles may be interacting with other things in their environment that's kind of sending them on this angled pattern. So because of that, even though we know the time, and if it traveled in a straight line, we would know the distance, we're not actually sure. So therefore, we can say that we know the distance, a distance, the delta D plus or minus, and then however uncertain we are in either direction. And that kind of accounts for our error of not being able to actually tell the true distance. And that comes in handy because it also gets to affect your momentum and your velocity and stuff, or your position and stuff like that. Because if momentum is just your mass times velocity, then that means we can't tell what the momentum is. And then if we really don't know what its final position is, we also can't really say that. And we just have to know that the difference in position, the uncertainty in position, and the uncertainty in the momentum is greater than or equal to Planck's constant over 4 pi. So that's a nice little constant side of the equation. And then again, I don't think we really like went into this too deeply, so I don't know how much is going to be on the final, but it won't hurt to know how to do 1 or 2 basic problems. And then this is, again, a little more in-depth of an explanation of why we have uncertainty in momentum, because momentum is just mass times velocity. And if we don't actually know how fast it was, how far it traveled in that certain time, we don't know velocity for sure.
Yeah, I remember because like I thought that he was gonna put that on the first midterm because it was like one of the harder concepts, but then he didn't. So then I was thinking like maybe he's gonna put it on the final now.
Yeah. So I didn't see any questions like that on the midterm again, but you know, you never know. And I've heard that it's kind of like a lucky bet for some of these tests on what questions you do get, because some of them are very like obscure conceptual. So it won't hurt to just have a basis in all of this and be able to do like a basic problem and then maybe a slightly more complicated problem, just so that you know that you have confidence in your abilities. But I think a lot of the Schrodinger was I think this was mostly just like kind of understanding. I think for these ones it was mostly understanding the concepts behind them rather than anything else. But still know how to actually like pull out the math for it if you need it. So the final of the big three is Schrodinger's wave function, and that's basically just to describe the orbital. So basically, where is the electron in the atom? And in cases we would use this is if we were trying to prove that an electron is or isn't in a certain area, how likely are we to find one? Because it's basically like, what's the probability that we're going to find an electron here in the center of the atom in this select orbital? So, and that would just be the wave function squared to find the probability. And I don't know if we really did much with this again, because it never actually showed up on the midterm. So that we had that going. But this was our last place for the very end of all the stuff we did for midterm 1. And we just tied it right into our midterm 2. And then this is just atomic orbitals, but we ended up talking about more of that stuff in, okay, wait, I'm gonna need to send more pictures in our next notes. So just give me a minute to send the next notes that I have. And I can show those too. And for anyone who's looking for like good ways to study, I would definitely recommend his little oh, okay, whatever, iPad. His little videos. I thought those were really handy. And then the textbook problems, definitely. I think the homework is like good for understanding the basic concepts, but I don't know if I've ever like found a super challenging problem on there. So just
What little videos are you talking about
um
besides the just the material for the first midterm?
yeah, just those
Oh, okay, okay.
I'm totally forgetting what he called them. His you know, where you had the pre-assessment and the video and then the nice little
Yeah.
post-assessment.
The
Like,
modules?
Okay.
yeah, the modules. There's the word. I can
Yeah.
chemistry, but I can't
So
English.
yeah. So that's just for the first like section of the information, right? Because I wasn't
Yeah,
able to find any part for like all the chemical bonds or anything like
no,
that.
but I definitely think for the first part, for the first midterm, those modules were super helpful because they definitely had a couple of good, like, challenging problems that made you have to think harder, both conceptually and just doing problems plug and chug wise. Okay. Chemical bonds, chemical bonds. Man, this was a big section. Okay, hang on. Give me 1 second. If this will take the picture like I want it to. this would be so much easier if I knew how to use technology properly. Okay. We'll say that we are doing this one. Okay, hang on 1 second. These are going to my computer. Okay, so I think those items came in. Let's get rid of this. I think some of my new ones came in, though I don't know what they all are. No. Oh, come on, send. Wait, hang on 1 second. These should be coming in right about now. And let me just plug in my computer before it dies. Okay. Okay, there we go. Okay, so I think we left off here. This is all material that starts for the second midterm. So we left off talking about the Schrodinger's wave equations and how those were just the mathematical equations really to find the orbitals. And what you get out of the equation is you actually get your n, so that would be whatever shell this is, your L, so that would be whatever the shape of the orbital is, and then your M, which is just saying like, oh, is it, I guess, up or down in this case, or no, I guess that's going to be the spin. The M is just the magnetic quantum, which is just telling you like what specific direction it would be in. So you have negative and positive values in that sense. So we didn't really talk much about that. That wasn't as important in this stuff, but just know that N is your shell. So N is 1, 2, 3, 4. And then that you have your shape, your orbitals, your 0, 1, 2, 3. It always has to be less than whatever your N is. So your 0 would correlate to an s orbital, and your 1 would correlate to a p orbital, and your 2 would correlate to a d orbital, and 3 would correlate to an f orbital, though there's more, but we just didn't go beyond that, so I don't think you have to know them. Though I have seen a question either on the test or in the textbooks that asks you what to do with the g orbital, and just know that once you start getting past these ones, the d orbital will always be in the level of, since d is d minus 1, f is f minus 2, or yeah. So that's how many levels it can go. This one can go down 1 extra level, this one can go down extra 2. So G, H, all the other ones just keep that pattern. And then dun dun dun. Your magnetic quantum, just know that I thought it was kind of weird how we sometimes talked about orbitals like this big thing, when in reality, the actual orbital, each select subshell has a certain amount of orbitals. So S only has 1 orbital, and P has 3 orbitals, and D has 5 orbitals. And I thought the best way to picture this, okay, here's a good way, is just as these little tiny boxes where each one can fit 2 electrons, and each of those boxes itself is actually an orbital. So just know that's what they're talking about when they say how many orbitals are in this, how many electrons can fit in this particular orbital. It's not just the whole general thing, like sometimes it comes across as we're talking about it, but it's actually just these little tiny smaller packages of 2. And then the final thing that we really have, I guess to explain this, we would have this, if this is a p orbital, we would have -1, 0, and then 1 here. So it's always just negative to positive, including 0. And then the final thing that you really have is you have your the direction that it's spinning, and that's either just up or down. I remember he mentioned that it doesn't really matter which way you start, so it's not going to be important if they ask you to like draw anything out, what direction your arrows are all pointing, as long as you're consistent. And then again, for when filling them in, you want to fill in, if you have a p orbital, or if you have a p subgel, which has 3 orbitals in it, and you're given 4 electrons to fill those orbitals, you're going to want to do it in the manner of one electron in each orbital that's all spinning the same direction, and then you can go back and you start adding the opposite spin ones. So a good example of that is what kind of down here is, instead of putting 2 here and 1 here, you want them spread out all across these boxes or all across the orbitals. And that's just because the principle that electrons, when they get super close to each other, will try to repel each other. So in order to create stronger bonds themselves and remain closer to the nucleus instead of being repelled out, they tend to try to separate evenly as possible. And therefore, you want to also separate them when you put them into the orbitals. So that covers all of the orbital numbers and anything like that. And you should know that no 2 electrons are ever going to have the same 4 quantum numbers, because each of those 4 quantum numbers is designed to tell you mathematically where a single specific electron is in an atom, in an electron cloud, anything along those lines. And then we kind of went over this, either that or was in the textbook, I don't really remember, but we never really talked about it in great depth. But basically, if you're dealing with not a hydrogen atom, there's more things that are going to affect the energy of E, because again, the less stable it is, the more energy it tends to have. So that would have to do with the distance between the distance between each electron, the positive and negative sides, all divided by the distance that it is. But I don't think we've ever actually had to deal with that, aside from thinking about it in the concept of shielding, where it's kind of like, oh, if this orbital is taking the brunt of that pull, then it's going to less so affect the outer orbitals. So basically, like, if there were 2 people standing in a row and someone had a squirt gun and they were squirting them, then only the person who's closest to them is really going to get the brunt of of getting wet. Kind of same thing for shielding, though if you wanted to get into it with more technical terms, it comes off a little differently than that, but that's basically the idea. And then again, the ones that we tend to deal with for electrons regarding any atoms is we just want the very outer electrons, the valence ones, because those are going to be very loosely held. Those are going to be the ones that are going to react if we launched a photon at it. Those are going to be the ones that are going to be traded or shared during bonding. So the main ones that we actually need to focus on are the valence, because the valence ones basically control everything else in chemistry that we've done or talked about so far. Dun, dun, dun. Okay, oh, I believe there was a question like this on the midterm, at least I believe I had one, but it was talking about nodal planes. So an s orbital has no nodal planes because it is in fact just a circle that has a nucleus in it. But for a P or a D or anything basically higher than that, there are nodal planes that cut through the nucleus, and prevent electrons from being there. So in the nodal plane, you're not going to have any electrons. So if it ever asks you a conceptual question, know that the only one that actually has electrons, the only orbital, the only subshell that actually really has electrons in the nucleus would be the S. And you guys can look up better pictures of how the p and the d orbitals and the f orbitals are shaped, but you'll see that they just kind of look like balloons that are kind of held together at the middle rather than just one big circle that encompasses the actual nucleus. Again, so that might be important to know. And because of that, you actually get different electrostatic interactions between the nucleus and the E in all these different ones, because the electrostatic interaction is again between the electron and the nucleus, the positive shell. So it's a distance between that. And then if you have a p orbital, then the distance of one that would say be on the outside right here would be different from one that's all the way on the other side right here. So you actually have a change in distance. Well, if you're looking at the s orbital, if this is the nucleus, anywhere you go is going to be the same radius away. So just because of the shape, it changes how the electrostatic interactions are affected. And because of this, we also know that s electrons have lower energies than p electrons in the same shell, which is kind of why we tend to fill those first. So it goes S, P, D, F, and then so on and so forth. And the only time that this like comes into question is if you actually look at a chart that's talking about the energies or the energies of each of these little orbitals, and we're dealing with D, which goes down one more level. So if you had so D tends to start on, I have a periodic table up, darn. Okay, but D tends to start, I believe, on like the third row of the periodic table, very, very far to the right after kind of P. So in those cases, just know that it's going to try to fill the D orbital in that quantum once you pass. So once you do, if you're doing N4, you're going to do N or 4S, 4P, and you also have this 4D that's going to go actually become a 3. So just don't get tricked by that, I guess. And then, dun, 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 writing electron configurations. Okay, so electron configurations, basically, anytime you have paired ones, they have opposite spin. So a paired one would be something like this when you have a full or more so than half full shell, then you're going to see paired. And it basically means that one has a positive spin, one has a negative spin. If you have parallel ones, then it just means that they're going to look something more like this, where you're not over half full. So you have one electron spinning the same direction in each of these orbitals. And then the Pauli exclusion principle is just the one that states you can't have more than 2 electrons in each of these little states. Oh, is stuff happening in the chat? Yes, if S, I believe that if S has lower energy, then it tends to be more stable. Because again, the way that we pull atoms out when we're sharing them is we're going to pull them from the higher levels. So we'd pull them from like the D shell over. There's a couple cases, the special case being that the D shell likes to be either half full or all the way full. So if you get the chance to either like, if you have 4 or if you have 9, then it might take one from the S just to fill it up because that would make it more stable. But that's kind of like an exception case. And then, dun, dun, dun. So basically no more than 2 electrons per orbital if each of these little squares is an orbital. And then Hund's rule is the one that says, oh, because electrons like to repulse each other or repel each other, we want to keep them as far away from each other if we can as possible. because this is going to give it the lowest energy and therefore make it the most stable an atom can be. And that's basically the stuff we do to actually get the ground state for our electron configurations. So I think my next page is this one. Yes. Okay. So when we're talking about building our or building our structures as in like writing them out, you always want to start with your first level and go on upwards. So you start with N1, you start with your S, and then you go N2, and then you do S and P, and then you do N3, S and P, and then you do N4, S and P and D, and all that stuff. So basically, it just wants you to build up. This is literally just a German word that says like build. And then once you start getting really, really high in your N, it's relevant to know that the difference in energy between each of those different subshells is going to get smaller and smaller, because there's only so much, because when you're originally close to the nucleus, you're going to have a lot of positive repulsion to repel those electrons away and stuff like that. But the farther away you get, it just kind of tries to stay close because you still get that attraction from the nucleus itself. Okay. And then here's the note about once your 4s state is occupied, then you get to enter the 3d state, and that the 3d state is actually lower in energy than the 4s state. So therefore, we're going to put it before, and it goes with its N3 group. And again, we talk about how D is always N-1, and F will always be N-2, and then G, if it ever asks, would be N-3, and H would be N-4. So just anything along those lines, if it asks you, it just keeps following this pattern the more you go up the alphabet of subshells. And then here's the exception that I mentioned a couple minutes ago, but basically, some elements are super stable when they have either 5 or 10. So they either have a half shell or a full shell in their d orbital, which is that kind of center, that central thing. So I think maybe aluminum might be one of these exceptions. I don't know. I don't really have like a periodic table in front of me or anything like that. But in that case, they tend to pull an extra electron from one of the s's into their d orbital, or if they can, they will be, if they have 6, they'll be more likely to lose one from that d orbital to try to get down to 5, because again, they'd be more stable, and therefore they'd have lower energy, or they have lower energy, and therefore they would be more stable. I guess I should say it as.
Just as like a side note, I think it's chromium and copper are the two exceptions for that we need to know.
Yeah, okay, cool.
Yeah. I remember there being that question on midterm too about,
Yeah.
I think for me, it might have been like, which one? I think it was copper for me.
Yeah.
Yeah, I got that one wrong. I got copper.
Just know that it's helpful to know these base ones, but know that they might not be the only exceptions. So if it asks you for the one that's in the row right below copper, then that might also do the same thing with the D block, where it wants to take one. So you can kind of apply it throughout. I don't think we've ever gone like super deep into the periodic table aside from like staying within the first 4 rows, So, yeah. But just know that if you ever do get a case like that, then they probably also follow that pattern. Because again, they just
I remember.
Yeah, go ahead.
Oh, sorry, go ahead. Oh, I remember on the midterm, it was like ground state copper ion, but it said like ground state copper 2+, and so then I ended up getting it correct, but it was confusing because like the way they worded it was weird. Like they're like ground state copper 2+ ion, and I'm like, how is it ground state if it's but then it ended up being like there's only one like lone electron, like unpaired electron, but like my other option would have been like 3 or something like that, because if they said they said it was a 2+ ion, then it could have meant that they like took away 2, but they said ground state. So I was like, okay, I guess we're not doing anything to it. I don't know. It was weird.
Yeah, I
Um,
definitely think there's definitely been a couple like weirdly worded questions that I'm like, oh, I don't really know what that means.
Yeah, because like I'm listening to all this and I'm like, I know what like I understand everything that's going on, which is also why it's so frustrating on the tests where it's like, I understand what's going on, but like, why would you say it like that? Because now I'm gonna get it wrong.
I would really recommend it if you guys haven't already, reading through the textbook chapters on this, because again, it's a
Yeah.
nice little review. It'll kind of cover everything we've already covered. And Lavelle only has so much time in his lectures to cram everything in. It's probably why we're going like 10 minutes over every single day.
Mm-hmm.
So reading the textbook kind of clarifies some stuff. There's good practice problems specifically for that subject. And I think that overall, like, it's just very good at clarifying patterns that we might see or extra exceptions that we don't really talk about.
Mm-hmm.
So,
what? Oh, sorry.
yeah, go ahead.
What was the correct answer for that one? Because I still don't really get it.
It was
Explain it
one
very well.
unpaired. It was one unpaired electron. So because the electron configuration of copper is going to be like blah 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 argon like 3d10 4s1, because on the periodic table copper, like zinc is where the 3d10 slot is, but copper wants to have a full orbital, so it takes one from the s or from the 4s orbital and fills it, so you end up having 3d10 and 4s1. And the reason it was kind of weird on the test is because they said like ground state copper ion, so then I'm of 2 plus, and I'm like, okay, so
Well, I think it is a 2+. Like when they say ground state, I think they mean like the electrons themselves don't get excited. So
yeah, that's yes. The correct
Yeah, but
that's why
I
the
think
correct
it would
answer is
still-
only one unpaired. Yeah.
Yeah, but I think it would be wouldn't it be like 3d9? Because you would still take out the 2 electrons. And
No. Oh well, I don't know, but I
because that would
think
still be one unpaired electron, right?
that's true. It still would
Yeah.
be. See, that's my problem. That was also my problem. I was like,
I don't think I had that one, but I think I like my guess would it would be 3d10 or 3d9, sorry, because you do have to take the 2 off.
Yeah.
Which is still one
Yeah.
unpaired, so it all works out the same.
right. They just like they don't, I mean, yeah, they just don't explain it. It just ended up was the like correct answer. Yeah. Okay, that makes sense.
Okay.
Okay. So just talking about that, yeah. Cations, cations, you're basically going to make it positive. And I guess that's because cats are always positive because you don't pause. Haha. Okay, well, anyways. I tried. Okay. Well, anyways, then anions are always going to be you're taking you're adding electrons, so it becomes more negative, and that's normally in the case of cations are going to be like these ones, where they're going to try to get rid of some of their electrons so they can move over to the noble gas state, which is the most stable because they have full valences, and your anions are going to be found over here for the most part, because that's where they want to get the 2 or 3 extra electrons they need to actually hit that full valence ground state. And then everything in here is just kind of like weird. So just see what the problem says. Atomic radiuses. Okay. Well, I guess we're kind of starting to get to the trend part, which there was definitely a few conceptual questions based on like the trends that atomic radiuses and ionization energy tend to follow. So know for atomic radiuses that they're just half the distance between your neighboring atoms. So basically, like, this is your radius. This distance here is just 2 radii put together, so therefore it's just half the distance. And know that as you go so they increase down the group. So as we go down this way, we're going to be seeing larger and larger atomic radii because again, each time we change rows, we're going to be jumping to a new subshell, and every time we jump to a new, or not a new subshell, a new energy level, and every time we jump to a new energy level, we're going to keep getting bigger and bigger and bigger and bigger. So know that as you go down and as our atoms, our singular atoms themselves get bigger, then our atomic radius is also going to get bigger. And then for cases like this, I believe it gets smaller as you go towards the right. And then I swear I have a reason for this, but I don't know if it's coming to the top of my head. I guess I wrote it down. How handy.
I think it's because of the number
Yeah.
of the atomic number.
Protons.
Yeah, so
number
the bigger the
protons.
nucleus, the more positive force we have to pull them closer together. So basically, as your nucleus gets bigger, your radius is going to get smaller, but as your energy level gets larger, it's just going to keep on growing. And I guess you can think of it as like the bigger it is, the stronger it wants to like hug it all together. Let's see if there's any questions. Oh, was there any questions? Okay. I just gotta check. Okay, so know this trend because I have a feeling that based on how many questions were based on just trends alone, we're definitely going to be seeing a few on our midterm. So another good trend to know, well, I guess we can also talk about other radiuses at the moment, but the ionic radius, which is just when you have an ionic bond, and it increases and decreases in the same exact way. So again, as you go down, it's going to increase, and as you go across, it's going to decrease. For the same reason, basically, as you have things pulling it closer together, the electrons closer together here, and you have just larger subshells or larger shells here as you go down. For the covalent radius, that's just two atoms bonded by a covalent bond. And I don't know if we really have to do much with that aside from knowing that about the size of cations and anions. So cations are always going to be smaller because when you get rid of that extra electron, you have stronger forces from the nucleus just pulling it closer and closer together, right? Because now that you have that one less electron, the electrons can all move around a little closer, but still be enough apart that they don't repel each other, and it just kind of squeezes it down all together. And then when you have an anion, when you start adding those electrons, they're going to try to repel each other, and they're going to try to make themselves far apart from each other because they're repelling by making the outer shell bigger and bigger. So just know that cations will always be smaller. If this is your normal lithium, then the cation, the positive, is going to be smaller, and your anions are just going to be bigger. And I would practice doing that with problems that have to do with like lithium plus 2 and I don't know, something that's near lithium plus 1, like different forms of cations and ions or anions. Because I believe there was a question like that on our midterm, at least on mine. And those would be, in the case of isoelectronic, those are atoms and ions, anything like that have the exact same number of E because they either gain some or they remove some. So if you're ever given a question, normally what we're given a bunch of isoelectronic atoms, and we get to try to figure out like what's going to have the biggest radius, what's going to have the smallest radius. So being able to follow that pattern and kind of understand this might be important. And then for ionization energy, that's just how much energy it's actually going to take to like free the atom and to free the electron from the atom itself. So we kind of see the trend that the farther away you have your electron from the nucleus, the easier it's going to be to remove. So therefore, because of that, we tend to see, because as we get down here and our atoms keep getting bigger and bigger and bigger, then we're going to see that it's easier and easier to remove our electrons each time, or our electrons down here, because they're so far away from the nucleus that that bond is really, really weak. It's like when you hold two magnets apart at a distance that they barely have any attraction. That's basically the case of what's happening here. So on that same note, whenever you try to remove your second electron, it's always going to be a lot harder, and your ionization is going to be higher, meaning that's going to take more energy to remove. Because again, once you get rid of the original electron, then it's going to do that thing where it has more positive, a bigger nucleus than the electrons around it, and it's going to try to pull it really close to it. And so therefore, it's going to be a little harder to try to remove it. And in cases of like anything neon gas or any gases, noble gases, they have crazy high ionization energies because they don't want to give away any electrons because they're at their full valence. So just know that anything that's really, really close, anything really, really close to this side where it's almost a full noble gas state is going to be really, really like willing to, it's going to be really, really hard to take away any of these electrons because they're so close to being a full valence. So they really want to hold on to them. And then anything over here, I always like to think of it as they're really willing to like let go of one of their electrons, because that means they get to go over here to the neon gas state, or the not neon gas state, the noble gas state. Okay, so then that's basically covering that, the fact that if you have low ionization energies, they like to get rid of one and they become positive, forming cations. And those ones tend to conduct electricity. I don't think we really ever had like a question that necessarily dealt with, oh, can we conduct electricity? But just note that some of the trends that kind of defines them is that they tend to conduct electricity in their solid state better. And then electron affinity is basically how much energy you release when you add that electron, or add an electron to a gas phase atom. So let's see if I can get to the next page. I think this one. I don't even know. It's one of these two. Wait. Oh my god, no. Why is it so big? Okay, wait, that's the first one. If this is the second one. Oh, I guess that was one of my last notes on it then. Okay. Oh, come on. Zoom in. Okay, so the next thing, oh my god, why? The next thing that we kind of covered in class would be, let's see if it lets me. Okay. This one. So kind of at this part, let me just make sure that was the last part of my note because I don't remember. Yeah, so basically the last two things that I had on that page, the last two things that I mentioned on this page here are that if your electron affinity is like, if it's something that wants to happen, if it really wants to like get rid of the electron, then it's going to release energy because you're bringing it back down to a more stable state, and more stable states are always less energy. But if it's one where you're kind of shoving it on there and it doesn't want to be there, it's going to require a lot of energy to keep that electron in its place, and you're going to get a very kind of you're going to get a more unstable atom. Okay, so that's basically the last bits of those notes. Okay, these ones. So this is kind of where we started talking about the bonds. And again, the bonds are just related to our valence electrons for the most part, because those are the ones that actually do make bonds. Okay, let's go. So chemical bonds are forming basically because you're going to have lower energy than the separate atoms if all of them can fill their valence, because any atom that's able to fill its valence is going to be more stable than one that doesn't have a full valence, which is why we see noble gases as never reacting with anything, really, because they're really stable, they don't need anything else, so they're not very good for reactions. While everything else that's kind of looking for either giving or taking an electron is something that we see a lot when we do chemical experiments and talk about bonds. So here, let's zoom in. So basically, if the lowest energy state that atom can do is if it's formed by an ion, so like it totally gives away that electron, or one totally takes it, then it's going to form an ionic compound. But if the lowest energy is achieved by, I don't know why I didn't finish this sentence, but I'm pretty sure it was like covalent bonds, then it's just going to be shared amongst them. And that normally means that they both still want it, but they also want one of the others that you get from sharing, if that makes sense. Okay, so just know that this is just supposed to be like covalent formations. So when we're talking about Lewis structures and Lewis symbols, then I think at this point, we all kind of had to know this for the second midterm, but you have your single E, your unpaired electron, and then we have our paired electrons. And then ionic bonds. So basically, ionic compounds, though, there's no true ionic or covalent, but certain molecules or atoms tend to show one trait over the other, if depending on what side of the periodic table they're on. So ionic compounds, for example, are going to really want to push away that extra electron, or one of them is going to want to really take it. So normally what we see this is in metals and non-metals. So the metal is going to try to give it away so that it can move into its so it can move closer to its full orbital, and then the non-metal is going to be the acceptor. And this is basically just getting an octet for each atom, which is, again, your octet is a full valence for the most part. So the exceptions for this is just going to be the first 4 octaves here. So hydrogen, helium, lithium, and beryllium, I want to say. I don't know why I don't know that one off the top of my head. Beryllium, yeah. I can do this if I have a picture, but I can't remember anything. Okay. So your main group metals form cations, and if you ever looked at the periodic table, the main group metals are, oh, I wish I had a periodic table. Well, anyways, if this is your periodic table, then they tend to be on this side, on the right side. And then so that's going to be where you normally find metals, where they're going to want to form main group metals are going to be on the left side, because those are like your alkaline metals and your earth metals, and they tend to want to remove an electron so that they can get to a full valence state. And then you have your p block nonmetals, which tend to form ions because it's gaining the valence electrons for its p subshell until it gets to its noble gas. So in that case, that would be anything on the right side. So that was my bad for saying that, but main group metals tend to be on the left side. So that would be like your alkaline and anything in your helium row or hydrogen row. And then p blocks are just gonna be on your right side. For covalent bonds, nonmetals don't really form cations because their ionization energies are really high. So it becomes difficult to actually remove that electron. So instead, what they try to do is to get that full valence, they decide to share with another atom or another molecule, anything along those lines. So that's what we get when we see covalent bonds. And again, note that no bond is ever going to be totally ionic, oh, what? Oh, you're gonna let her in? Okay. Okay. But no bond is ever gonna be totally like ionic or totally covalent, but they may lean towards one over the other. But we can see both traits in every bond. So drawing these structures, I think we have a pretty decent practice doing this because that was like all homework. The last like a bunch of the last 2 homework assignments had drawing stuff in it. But anyways, for drawing them, what you do is the steps are to count your valence electrons based on where they are in the periodic table, or like if they're a cation or anion. And then you're going to try to pick the one with the lowest ionization energy to put in the center. So that tends to be like C, if you can, ones that bond well in the center. And then if you ever have hydrogen, that's just going to be at the very outside because it only can make one bond, so it's useless to try to put in the center. Those are for protons, so we talked about that. So the resonance is basically like the multiple bond possibilities. So in this case, there's a resonance structure of you can have double bonds here, or you can have double bonds here. And what it actually is, what the full representation is that it's a combination of all the resonance structures that you make. So it's just a blend of all of them, and that's what's going to represent the actual structure. Because if we look at like when we calculate the total distance of bonds, or like the average distance of bonds, we see both like, oh, there's a double and single bonds in there. And then from that, we can kind of, in problems like that, we can kind of say, oh, because it's slightly lower than being in between single and double bond numbers, length numbers, that we can say it's going to have more of one bond than the other. So that can help you decide like which structure would be the most accurate, I guess, or the most plausible based on bond length. And then we call any of these electrons in here just delocalized, which just means that like we can't say for certain that it's there, but we know that it's somewhere within these bonds, within this loop. So this is just another way to represent it, is a resonance hybrid is just drawing like, I guess, a hexagon around it if it has 6 bonds. Okay, so says the resonance just through different structures with different arrangements of the electrons, so different bonds. The resonance structure is useful because it's taking all these bond characters of like a double bond that would be here and a single bond that would be here, and it's kind of spreading them out, which is overall lowering the entire energy of this big molecule. And then when we talk about formal charge is, for the most part, it's telling you whether you either like gained or lost an electron when you made this covalent bond. So to actually find the formal charge, you have your valence electrons of the atom minus your non-shared electrons. So that would just be like, oh, if I had an electron pair out here, that's what I would subtract, minus any bonded electrons divided by 2. And the best way to create any Lewis structure is to try to have the least amount of formal charge you can. And when you do have formal charge, try to make it plausible by putting like a negative formal charge on oxygen, which has a tendency to want to take extra electrons. You know, so if there's ever a close call between 2, you can kind of look at the periodic table and say, yeah, this one would be more likely to have a negative value to it, or a negative formal charge. the shortcut for formal charge? And if you do, could you explain it?
It was the one where it was like the charge of the atom minus things minus. Does anyone know what I'm talking about?
Yeah, I remember. Was it Justin who was talking about that?
Yeah, I heard
Um,
it from a few of them, but I just can't remember it exactly.
I think what it was the number of valence electrons still, and then it was minus things, and so a bond would count as one thing. I think. Yeah, so like a single bond would be one thing, a double bond would be two things, a triple bond would be three things, and then each electron in the lone pair counted as a thing. I'm
Oh,
pretty
okay,
sure.
yeah. Yeah, that
Okay.
sounds
Because basically what all it is like the bonded E divided by 2. So that's basically like the things is just the simplified version of that, I think, where like a single bond instead of 2 divided by 2, it's just one thing.
right. Okay, that makes sense. Thank you.
You're welcome.
Right, cool. So again, with formal charge, we want it to be, if it's at its most stable state, then we're trying to get it as close to 0 as possible. So if it ever gives a question of like something that has like a +5 formal charge and like a +2, your +2 is probably a better option. And one of the things about bonding is that if you have a d orbital, which is kind of after phosphorus on your periodic table in row 3, then you can have more than an octet bonded because you can start putting those electrons into your d orbital. So any other octet exception is radicals. So these are basically any compounds with this unpaired electron attached to it, and they are super, super reactive. So if you wanted a really quick reaction, then you deal with radicals. But because of that, because they're really highly reactive, that means they have a lot of energy. They're very unstable, so they don't last very long. And then for any Lewis acids and bases, group 13 elements, if you're going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, like across the periodic table from left to right, then group 13 elements tend to need 5 electrons to complete their octets. And then special cases, B and Al react to the Lewis acid base react in Lewis acid base reactions, and basically it becomes lone pair acceptors because it needs another atom to provide both bonded electrons for a coordinate covalent bond. So in those cases like that, it would, I guess a good case would be BF3, I want to say, where instead of bonding again with a another F, or double bonding with an F, it waits until another one comes because the F doesn't want to bond. So you have to have something that brings both to the table. Okay, so for acids and bases, know that the lone pair donor is always going to be the base. That's the one that's going to like give the pair away. And the lone pair acceptor is always going to be the acid. And that leaves you with, this is kind of like a picture of it. But I guess if your base is the one that's going to give it away, here's your acid that's going to be taking it. And that is what forms your like acid-base complexes, your Lewis acid-base complexes. So for ionic versus, let's zoom out again. Ionic versus covalent bonds, like I said, a lot of these bonds have both ionic and covalent characteristics. Some lean towards one more than the other though, but for the most part, it's a mix. So because of that, the electron pair that's in the covalent bonds isn't always equally shared, because if you have an atom that has a stronger pull towards the center, then it's going to try to pull that electron more so than its partner. So atoms with a closer electron pair tend to be slightly negative, so like H2O is kind of what we see this, and while others tend to be slightly positive. And that's just because like there's a difference of electronegativity, which is how well it can attract that electron to it. Okay, next page. Yes. So this kind of comes into play. Ionic versus covalent bonds. We are right here. Okay. So we kind of tend to see, because of that, a lack of equal sharing. So that's where we are able to kind of start creating like our hydrogen bonds from, or having dipole-dipole interactions, because there's a difference in charge. So if the ionic energy and the electron affinity are both high, then the atom is going to tend to have like a really high electronegativity, and it's going to want to pull a lot of the atoms towards it, because this is basically saying if it doesn't want to remove an electron, but it really likes to like take electrons, then it's going to pull that electron a lot more than other atoms compared to it. But the opposite is true the opposite, vice versa, is if you have a really low ionization energy and it's really easy to take away an electron, and you have a really low electron affinity, like it doesn't really attract any, then it's going to more likely have that electron that's being shared push towards the other one that's going to be more electronegative. So it's kind of like a game of hungry hippos here, where the one that wants it more is going to try to get it more and therefore pull it closer. And the way he told us to kind of like decipher between if it's an ionic bond and a covalent bond is the electronegativity difference between the two atoms that are in the bond. So if you have a really, really high difference that's greater than 2, then it gets to the point where that atom is almost going to completely leave whatever it's being shared between, and it's going to become an anion and a cation who are attracted because of the different charges. But if the electronegativity difference is like less than 1.5-ish, the covalent, it's going to be more like a covalent bond because it's going to be more evenly shared. And the way to kind of decipher this, if it ever asks you, but it doesn't give you its the actual electronegativities of the values, is to kind of look about where it is on the periodic table. So if you have something that's on the very left of the periodic table and you have something on the very right of the periodic table, then they're going to tend to have a higher electronegativity difference than something that's kind of closer together. So I would look at if you guys could, like in your free time, just a couple of example problems of what gets decided as either covalent or ionic, to just see that pattern in action, because I think that's very helpful, because I do believe there was a problem like that on the midterm. So there could be one on the final. And then for this part, okay, so basically in cases of we see this a lot for ions, you have polarization occurring, which basically means that if this is, we have to think of electrons kind of as like an electron cloud, where it's just a general area where all these electrons are. So if you have something that's very, very positively charged, then it's going to kind of distort that cloud and pull that cloud towards it, since that cloud is very negative. So in this case, if you have a cation over here and you have an anion, then a big electron cloud is going to kind of move towards the positively charged cation, because opposite charges attract. So that's just what we kind of refer to as having like a high polarizing power, which basically means like it's the one that causes distortion. So anything that is able to really pull and warp the electron cloud of its neighbor towards it has high polarizing power. And that tends to create a little more of a covalent characteristic between ionic bonds. And then again, another thing that affects it is if you have a really big radius. So if your nucleus is here and you have such a really big radius, it's not going to be able to hold on to those electrons as strongly. So again, it's easier to distort them. Okay, so that is that chapter. And I think I have like one more page of notes about bonds. And then we're all caught up to the second midterm. Okay, charge distribution in molecules. Okay. Yes, this is all about bonds. Okay. So the way that you actually like distribute your electrons is going to affect the shape of whatever protein you're dealing with. And that's mainly because, again, like they tend to it's going to, the distribution is in the form of bonds or is in the form of opposite charges. So it might kind of move to where it would be the most stable. So for most proteins, they probably want some form of stability, and therefore you'll see like more double bonds and triple bonds and single bonds. But for weaker proteins, it might only have like a single bond, and therefore it's able to rotate a little more and move around a little more. So it's a little less stable. But because of that, electrons are able to kind of like influence how proteins get shaped. So this section was just basically all about bonds. So our polar covalent bonds, it's just cases where the electron isn't equally shared. So we would see cases like that if in the H2O molecule, where O tends to pull it closer and H becomes slightly positive. And then that's basically just an increased difference in the electronegativity causes an increased difference in the charge that each atom in that molecule tends to get. And therefore you get more of an ionic character in the covalent bond that's present, because it tends to push or pull that electron further and further away from the middle. Your charge differences are normally measured in this electric dipole moment, which is measured in this little symbol mu. And the dipole moment the dipole movement is just the absolute value of the charge multiplied by whatever your bond length is, or your distance. So I don't know if we ever actually like saw any questions that dealt with that specifically, but it couldn't hurt to know if it asked like what has a greater dipole movement, or what has a smaller dipole movement, when it asks you to compare and contrast them. And the way we actually represent that is just the arrow that's pointing to where the E's are going to, or the electrons are going to go. And then you have a little cross here to make it like positive for the more positive side, because you're losing electrons. Okay, so this is kind of where this stuff is going to be pretty important, because this is all just about bond strength and like what type of bond is present. So of course, if you only have a single bond, it's a lot easier to break than if you had a double or triple bond. And then those double and triple bonds are also going to be a lot shorter, because they're going to be sharing 2 electrons among, or I guess 4 electrons, and they're going to pull each other closer together. And therefore, they're a little less reactive, they're a little more stable than if you only had a single bond. So the way we actually measured like the strength of a bond is by the dissociation energy, which is just the energy needed to break that bond itself. So the longer the bond, the smaller the energy required, because it doesn't take that much to actually break something. So I guess you can kind of think of it as if you only had a little tiny thread that you had to cut compared to a really big thick rope, then that little tiny thread would be like your weaker bonds, a single bond. And it's really easy to cut, but your big thick rope would be like a triple bond, which makes it really hard to cut, but very stable. So another thing that might affect it, if they come up with like conceptual questions, is that lone pairs on the neighboring atoms actually repel each other. So that makes the bond slightly weaker. So if it's ever a close call between 2 bonds, then you could look at their lone pairs and see if they actually push against each other, because that would push the atoms further apart and make the bond longer and therefore weaker. So in any interactions between ions and molecules, you have basically like intermolecular attraction, which is why we tend to see like liquid and solid states where they're very, all the atoms and all the molecules are very, very close together because they're all being kind of attracted to each other. And then we also have a lot of these interactions that are actual types of bonds that are these attractive forces. So you have your total ionic bonds, which is a cation and an anion. And these have very, very, very high energy. So you need a lot of energy to like break apart. In this case, you can see it's 250 compared to like the next strongest, which would be hydrogen bonding, which is only 20. So that's like an over 200 plus difference in energy needed. And then our next strongest would be hydrogen bonds, which are just like, they're basically, hydrogen has special properties that allows it to bond stronger than its normal dipole-dipole forces. And then we also have ion dipole, which is like, in the case of, you have a negatively charged one attracted to the positively charged like hydrogen on H2O. So that would be like, oh, there's a slight ion interaction going here because the chlorine is negatively charged, and the dipole is just like it's slightly sharing. It's kind of just attracting each other, but it's not actually pulling any electrons away completely. Dipole is basically like in cases of HF and HF, so it has like a pretty low energy to actually like break that bond. So again, it's not very strong, but it's definitely a lot. It's pretty similar actually to dipole-induced dipole ones, which is basically like a positive and negative of one is going to influence the electron clouds on another. And therefore, you're going to get kind of a slight positive and negative charge attraction that doesn't actually act as a bond, but just does help make the molecules move closer together. And for dispersion forces, I believe we talked about this, like they're in every single molecule we see, it's just the temporary movement of the electrons in the electron cloud that make one side slightly positive and one side slightly negative, and then that changes again. So we tend to see that in our like van der Waals forces or London forces. And so again, your weakest force is going to be dispersion always, and your strongest force is going to be ionic. But when actually dealing with non-ionic bonds, then it tends to be hydrogen bonding, which is why we see water as like something so special, and hydrogen is such a special element because it has the ability to bond to the O and the N, and there's one other letter, but I can't remember it. There's one other element, but I can't remember it off the top of my head.
Fluorine?
Yes, fluorine. Okay. So basically, dispersion forces will always be there. So if it asks you what type of forces are present, then you can look at what type of attraction is going on. So dispersion forces will always be there. And then if hydrogen bonding is present, then it's just a special form of like dipole-dipole. Okay. Again, dispersion, just a fluctuation in the electron cloud density. And then this was either in the textbook or in his lecture, but it was just talking about the polarizability of atoms as the interaction potential energy. So it's just the polarizability of both atoms divided by the distance between them. And I don't think we ever really like did very much with that, but if you want to know about it, the polarizability depends on like the size of the atom and the number of electrons that are actually in it. So like the bigger a cation is going to be able to, it has a lot more polarizing power than any anion because the anion is very big and spread out. So I think we talked about that like a little earlier in like the last page of notes, So just something along those same lines. And just know that in cases of interaction potential energy, the radius does have a big effect on it, because if your radius is really, really, like, depending on how far the distance between your actual atoms and molecules, then it's going to have a big effect on your interaction potential energy. Because as this gets higher, we're going to get closer and closer to 1. So if your radius is really big, we're going to have a closer to 1 answer. But if it's very, very small, we might have like a multiple number, like a larger interaction potential energy. Okay, and one of the main things to know about this is that, like, increasing the size and the mass of the atoms and the molecules is going to overall get you a stronger interaction potential force. So one of the things I do remember him like talking about, but I don't think we saw it on the test very much, it's just that the shape of the molecule also contributes to the strength of the interaction. And that's just because if you have more area for the electrons and the charges to actually interact with each other, it's going to be stronger. So here, if you have like two very disk-like ones, then you see all these different interactions that are occurring. But if you have just two spheres, then you're not going to have that strong of an interaction because there's less parts that are close to each other. Here, there's less parts of each atom that's close to each other. And one of the things about this might come in handy with answering a couple questions, because the stronger your interaction force is, then the higher the boiling point is. And I did see a couple questions in the book that like asked about boiling points and melting points. And for those cases, you would look at like it's hydrogen bonding, it's the bonds that hold it together, and then any like interaction forces. And you could kind of tell which one's going to be harder to boil, harder to melt. And then we have a whole little special part based in hydrogen bonding, because it's just that hydrogen is covalently bonded to a very electronegative atom, and therefore it's going to get this let's zoom out so I can actually see all this. It's going to get a very like positive charge. So in our most common case, we see water, which is why water is so important to like many interactions we see today, is because your oxygen is very electronegative, so it kind of gets this partial negative charge, and your hydrogen therefore takes a partial positive charge. And because of that, you have attraction between a partially negative hydrogen and a partially positive hydrogen, my apologies, and a partially negative oxygen. Okay, and then again, that's just a very special form of a dipole-dipole interaction. So if you ever, if it's a question ever asked, what does this have, and it has hydrogen bonding, then you can say, yes, it has dipole-dipole interaction. And then you could be more specific by saying it has hydrogen dipole-dipole interactions. And this is actually one of the most important ones because it's like weirdly strong, and it's also going to be very important for the shape and for, again, your boiling points, your melting points. So basically how your element's going to react to a change in its surroundings. And I think that covers all of the notes up to midterm 2. So does anyone have any questions?
Is this, wait, I think I see, is it being recorded?
Yes.
This, okay. Where can I, because I like missed the first hour and like the quantum stuff, I need, where can I find it?
I will try to post it in the group chat. Like, I don't know, I'm thinking about maybe just making a document to put in like the group chat, like the bio thing, where it's just links you to a Google Doc that has all of the other links for this class on it.
Oh, sweet. Okay. Wait, oh, have you done these before?
Have I done what? These study sessions?
Yeah.
No, but I was thinking like we could have a link for like the test bank and a link for the worksheet bank, the UA worksheet bank, and a link for like the lecture recordings or the study session recordings, just to make it a little more easier to navigate.
Yeah, thank you so much for this. This is like super helpful. I
Yeah.
totally thought you were like a UA for a second.
No,
Like, so
no,
like,
I'm not. I'm a chemistry student. I've never hosted a Zoom meeting before in my life, so we got that going for us.
Well, thank you.
Okay, so that basically covers all the notes on going over it. So I think what we can do now, because it's been what, like 2 hours. If you guys want to spend like half an hour going over a couple, like a few select problems that we pick out, the textbook has some good ones. The modules have a few good ones. So let's see if I can find any, and we can kind of practice some of these skills again, but it definitely wouldn't help to do 1 or 2 problems for every topic that we've learned. I guess I can just close that. I don't know what happens if I close that. Dun, dun, dun.
I have to head out, but thank you so much for this review. This was really nice.
Yeah, and I'm gonna do one tomorrow for all the new stuff that we've learned.
Oh, sweet. Okay.
So at the same time, I'll post another link on the chat and I'll like remind everyone. But I'm just gonna do one. This is like basically final prep. So we're doing everything before, and then I see a lot of people struggling with like the new topics. So I thought I might just like dedicate like a full 3 hours just to that one,
Okay.
or the full 2 hours.
Coolio.
Yeah. Okay.
All right.
Well,
Thank you again. Bye.
yeah, no problem, no problem. So I think a good one is a good one for dun, 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 properties of light, I believe, or the photoelectric effect. Wait, let me look. I took notes on some of this stuff. Oh, let's see what these say. Chat. Okay. Okay, so let me look at some of the problems that I thought were useful. Okay, so I would say that, again, if you haven't done them already, definitely go through, like, I know it's a lot of work, but read the textbook, do the textbook problems, and then, like, if you can, just go through the module questions again, because I think they all are pretty similar to what we saw, and it gives you a good, like, memory boost for all this stuff. Okay, do the 3 other people here want to stay and do a couple practice problems? Or I can host a session like later on next week where we just go through and do a bunch of practice problems, and this can just be more like a summary session.
Maybe that might be best.
Yeah. Okay. So I'm
down either way.
yeah, I'll let you guys, because I was planning on hosting the 2 this weekend and then 1 on Saturday before our big midterm, because we like midterms on Sunday. Yay.
Yeah, well, that also makes sense to do like problems the day before so they're fresh.
Yeah. But
Yeah.
just the best advice I can give to like literally everyone here is make sure that you like actually go through and do the practice problems even if you've already done them again, and just go through your notes and kind of see what you're still confused on, and then make sure you know any of the really heavy like conceptual type of questions, like what happens with ionization energy, what happens with the radius, what type of bonds would we expect to have if we saw this, because I feel like that's what most of our final is going to be so far, since midterm 2 was heavily conceptual and midterm 1 was kind of like reasonably conceptual with a couple like actual solve it out problems. So that's my recommendation to you guys.